Okay, I guess let's get started. This is my agenda for today. Not a whole lot. I don't know if you guys can read this. I'll someday figure out how to actually increase the font size in this Emacs. But basically, you should have received proposal feedback. Has everyone received it? OK. Some of you are rewriting your proposals based on that. So it's actually some of you have sent it to us. So you'll receive feedback on that as well. But basically, please push forward with your projects, taking into account all of the feedback. That's the fun part of this course. Actually, everything should be fun in this course, but that's perhaps the most exciting part of this course, because you can do some research and actually get to publish it if you take the right steps. Everyone received the feedback, right? Including the remote students who are listening to this right now. OK, good. That's important. And keep the TAs engaged. Like it's very easy to not make progress and delay progress until 2 weeks before the final report is due. It's not going to work like that in this course. It's not that way, because the project is a major chunk of the course. So keep making progress. We'll have milestones on literature surveys, and we'll give you timelines for that. But we cannot keep pushing you forward. Treat this as more like a master's or more like a PhD project, actually. This is a graduate course, so you're expected to be a little bit independent. It's not that structured, right? So it's important. I'll keep reminding you of this one. But keep the TAs engaged. Keep me engaged also. Whenever you have questions, please email me if you need help. But email 740 official in general so that you can receive the fastest feedback. OK, you should have received review feedback also. Has everyone received it on their reviews? OK. So what we're doing is basically chunking your reviews and giving you overall feedback on your reviews. Overall, I've been pretty happy with the reviews. If you can be more critical, that would be good. It's good to try to find out what are the weaknesses and what are different ways of solving the problem. There's no perfect paper in the world. Every paper has a weakness. Every paper has a strength also. So it's important to acknowledge the strengths. It's important to be positive about what the authors are trying to do. But it's also important to be constructively critical. Critical in the sense that how else can you solve the same problem? Or what are some of the shortcomings in the approach? Can you improve upon them? So this is not necessarily in a negative way, but in a way that's constructive, such that you can improve the state of the art. Because if you not have this kind of critical thinking, then it's very difficult to improve the state of the art, right? And everything is done. You don't want to be necessarily in that camp if you're a researcher, because everything is definitely not done. We can still innovate significantly. That's how you can achieve big things. That's how you can design new systems, right? If everything has been done, then we wouldn't be designing new systems. But that critical thinking enables you to design new systems. And this is my major feedback in overall, being like more critical, as well as thinking about very different ways of solving the same problem. For example, when you read a paper, think about a different approach, not necessarily the approach advocated by the authors, because that will enable you to think differently, think out of the box, if you will, and generate bigger ideas that way. OK. But everyone received the review feedback, right? OK, great. There's a calcium seminar next week. I'll point that out also before we go into other topics. If we search for calcium seminars, actually, this should be on the course webpage as well. You might have attended yesterday's seminar, A Path to Achieving Sequential Correctness for Parallel Programs. Next week, there's Design for Security, the Hardware Up Principle by Professor Setu Madhavan from Columbia University. So you can go and look at the abstract. It'll be a seminar about security, and he actually provides some paper references as well. So you can take a look at that. So we won't talk a lot about security in this course, but if you're interested in this topic, there's another area where you can do a lot of research on. It's an important topic. Providing hardware primitives that can, on top of which people can design secure systems is very important going forward. And Sima has been working on this, so he'll be talking about that. I look forward to his talk, so hopefully you'll attend it also. And while I'm at it, we can check I guess 740 EC CMU. What happens if we do this? Not courses, I don't want that. Actually, maybe that. There you go. So do we have links to the seminars here? Talks? OK. There you go. Yeah, you can find calcium seminars over here. And yeah, while we're at it, we'll have a guest lecture on self-repairing architectures Monday, the 21st, 7:30 to 9:30 p.m. So please attend that. And you'll see there are papers assigned for that lecture. There are a bunch of references. So this is another lecture. This is about reliability. We talked about security very briefly. But another thing that we will not get into a lot of detail in this course is reliability, how to design reliable architectures. But we'll have a guest lecture that's going to cover that topic in some detail. And these are some of the papers on that topic. So definitely attend this guest lecture. So this could be part of the exam as well, by the way. If this is not enough motivation, maybe the exam part will be motivation for some of you. But you're not here for grades anyway, right? We've settled that before. OK. I'm sorry? So that's a great question, actually. The exam, it's not going to be on October 18th. It will. We're still figuring out a time for that. It'll be October 23rd or 25th during class time. OK. So this is right before the exam. You can you can keep your brain cells active, and you don't need to refresh them. Hopefully, it's like DRAM refresh, right? You'll need to refresh your brain cells once in a while so that you remember the information. I guess humans are not that different from computers. OK, so this is October 21st. And there's a calcium seminar by the same person, Dr. Lee, Yanjing Lee, on self-repair of on-core components. So this will be a much more focused seminar at that time. And you can read about that, too. That's on the 22nd. OK. OK, let's see. Yeah. I guess any questions related to this? Any questions from lectures? I promise that I will cover rethinking memory system design. It's kind of an overview of the topics that we're going to cover in the memory hierarchy lectures if you haven't started them already. And you can ask some of the questions while I'll talk about that too. Is that good? Yes, you have a question.
I have a question on the sequential consistency seminar. I didn't attend the seminar. I only read the intro to the paper.
OK.
But the intro to the paper did not convince. It wasn't clear why would you want sequential consistency proper.
I see.
Why would mainstream programming benefit from it? It seems like usually you don't really care.
So in the calcium seminar, you mean?
Yeah, right.
Yeah. So that's because of the reasons that we've discussed in class. You watch the lectures, right? Yeah. Maybe the intro to the paper. I don't read the paper either. Oh, so the question is the intro to the paper that was presented as part of the calcium seminar did not really motivate why sequential consistency is needed for the programmer, right? Actually, I didn't read the intro to the paper also, so I cannot vouch for that paper. But maybe the paper assumed that that's a good characteristic to have because of what we've discussed in lectures, actually. Because if you don't have sequential consistency, it's very hard to reason about the ordering of operations. Remember in the lecture, I've given you an example of two critical sections. And if you don't have sequential consistency, you can get the wrong result.
But you almost never write code like that.
So that's a good question. You have a very good point, frankly. At a high level, as a high-level programmer, that could be true, actually, because you really may not deal with that level of abstraction. You're at a much higher level of abstraction. For example, you use constructs like synchronized in Java, and that has nothing to do with that level. So I think you're absolutely right at that level. But there are programmers who write code at the lower level. For example, those programmers who write the libraries for synchronization. And they do want to optimize the code. And those are the people who write that kind of code. And they should be able to reason about the behavior of the hardware very well. If they don't get the library correct, then all of the code that that builds on top of that would be incorrect.
So what are some examples at that lower level where you need to, because usually you use just compare and swap or some of these atomic operations which are not affected.
So they could be affected, actually. Compare and swap could be affected. I'd encourage you to think about that. It takes a while to go into that detail. But those operations are effective if you don't have sequential consistency. So atomicity helps, certainly. If you increase the granularity of atomicity, that atomicity actually kind of enables consistency, right? Because you say atomic, it's all or none. But it doesn't say much about ordering. OK? So the example that I gave actually was very similar to condition variables, right? You're basically setting a condition variable and checking that condition variable. And a lot of people still write code with condition variables, because that enables a thread to continue if some other condition is set by some other thread, right? It's like the full empty bits that we've discussed. If this memory location is full, now you can continue. You can use that and get into your critical section. Right. Does that make sense? Does that answer your question?
So I guess there must be ways to implement condition variable primitives without sequential consistency, right? Because it seems that most of these current machines don't have complete sequential consistency, right?
Exactly, yes. So there are ways, which is basically what we briefly discussed in the lecture also, memory fence operations, for example. Programmers put memory fences before some of those synchronization operations that require ordering. And if you put the memory fences at the right places, you don't need a sequentially consistent machine. You just have consistency at the boundaries of those fences. Now the hardware can optimize nicely for the other parts of the programs. Yeah. But these are very good points, actually. These are the points that have been discussed over and over for the last 30 years or so in consistency. OK. Any other questions? Yes?
When we say instructions, like when we calculate IPC, something like that, so what does the instruction actually mean? Like, does it mean one line of like one instruction in the assembly code, or like one trace in CPU, like load?
Wait, which instruction actually exactly means?
Yeah, like when we say IPC, calculate IPC, so what that instruction means, like.
I see.
Is it an instruction in the assembly code, or it's actually a trace, like load, store data? Like that?
Basically, instructions per cycle, right?
Yeah.
The question is, what does an instruction mean in instructions per cycle?
Yeah.
Well, basically, it's an instruction in the assembly code, right? It's basically an instruction that's specified by the ISA. If you look at the ISA manual of x86, for example, there are a bunch of instructions that are specified, and instructions, an add, for example. Right? All of the instructions that constitute the program will affect your IPC. Now, how do you compute IPC? We've had this discussion earlier, I think, in one of the discussion sessions. Basically, it's the retired instructions per cycle. How many instructions do you retire or commit to the architectural state per cycle? Now, that means that you need to look at all the dynamic execution. So you don't count the instructions in the assembly, obviously. You count how many instructions are retired by the machine. So that's one performance measure, basically, instructions per cycle. It's part of the performance equation, right? It's not the entire performance equation. So if we go back to this very briefly, your execution time, let's see if this is visible. I guess it is. Oh, that's visible online also, right? OK. I did not see what's online, but I guess it's supposed to be the same thing as I see here. So it's really instructions per cycle. Actually, I did it the wrong way, but that's OK. Times time per cycle. I guess, let's see. That didn't work right. OK, let's start. Let's start again. It's really, you have number of instructions, right? You have some number of instructions to execute. And each instruction takes some number of cycles, right? Cycles per instruction. And each cycle takes some time, right? Time per cycle. Right. That's your performance equation for a given program, right? Now, eventually, you get time. You eliminate these. So basically, instruction per cycle is part of that performance equation. And you're trying to, assuming that number of instructions and time per cycle is constant, you would like to minimize cycles per instruction or maximize instructions per cycle. Which means that this instructions is the number of instructions in the program, right? Now, you could always think about redefining this equation in somehow in a different way. Let's see, you can actually say amount of work, for example, right? And you can think of cycles per work instead of instructions, right? So for example, in some of the papers you read, we don't look at instructions, but we look at micro-operations, which is not visible to the programmer, which is basically part of the hardware itself, right? We look at how do you maximize micro-operations per cycle. I don't know if this is focused enough. Let's try something. Is this better? It did something. OK. Yeah. So basically, it's a measure of how much work you get done in one cycle. Does that make sense?
And if there is a branch prediction and we execute on the wrong and mispredicted the path, then the instruction on that path is not
counted. That's right. Because those are not retired. Those are not committed instructions. You look at committed instructions.
So not all instructions have like the same time, because I mean we don't consider about the cache means or something like that. So some instructions take longer time. Like if you multiply something, it will actually take more time than a bit shifting.
That's right. But those will be counted in the cycles, right? Mispredicted path will be counted in the cycles.
So what if we have a program like all it has a lot of adds, and the other program has a lot of multiply? So it's not fair to compare them.
Well, you're comparing apples and oranges then. That comparison makes no sense, right? Why are you comparing program A versus program B? I guess I don't understand the question, maybe. Maybe the question is, if you have the same program and compile it in two different ways and still get the same effect, then you cannot compare cycles per instruction, right? Then what you're doing is you really should be comparing execution time. Right? This is just a heuristic to compare different architectures, assuming these two remain the constant, right? If these two don't remain the constant, you cannot just compare cycles per instruction at all. Does that make sense? Yeah. It's really execution time that we're really comparing. When we try to execute like the same amount of work on different architectures, or maybe with different programs, you should really be comparing the execution time. OK? Yeah, you can look at some of the metrics lectures from 447 that discusses some of this. But yeah, you've got to be very careful with the comparisons. So it's really, so I think going back to your branch misprediction part, this is really, what you're really doing is cycles times time per cycle, right? You could express this equation that way also, right? How many cycles it takes to execute the program and how much time it takes to execute one cycle. Then you don't really care about the instructions, right? You have some constant amount of work to do, and it takes so many cycles, right? And if you have branch mispredictions, basically you're consuming cycles without retiring instructions, without doing useful work at least. Right? So that adds up to your cycles. So this cycles can be broken into this way also, right? Number of instructions times cycles per instruction. Basically, you're amortizing the cost of all of your branch mispredictions across all of the retired instructions. That's what this measure means, cycles per instruction. Make sense? OK. OK, what else? Yes?
With sectored caches, are there any advantages in terms of coherence?
With sectored caches, that's a good question. So with sectored caches, basically what a sectored cache is, we've discussed actually in the brush-up lectures. You basically have valid and dirty bits at a granularity smaller than your block size. Right? You keep track of the tags at a larger granularity at your block size, but you have sub-blocks, and at the sub-block granularity, you keep track of valid and dirty bits. Now this enables you part of a block to be present in the cache and part of a block not to be present in the cache. So this is separate from your coherence granularity. You can have a sectored cache that enforces coherence at the granularity of the block or sub-block. So if you enforce granularity at the sub-block level, then there could be advantages in terms of coherence, right? So let's take a look at a sectored cache, I guess. You have a tag, and then you have, I guess let's say, you have 4 sectors, right? I like thinking of a sector cache this way. Val, dirty, val, dirty, val, dirty, val, dirty, for a write-back cache at least. This is your tag store, right? For a four-way sectored cache. And then you have your data, although it's going to be bigger, but I'll write it this way. And this is your data store. 1 tag and 4 valid and dirty bits. Now, if you're keeping track of your coherence at the block granularity, which is the tag, then sector caches will not have any advantage, right? Because you would be invalidating your cache blocks at the granularity of the block. But if you're actually keeping track of your coherence at the sub-block granularity, now you might have an advantage, right? In one cache, you might have this sub-block dirty. In another cache, I'll draw this. Another processor's cache. 1, 2, 3, 4. You might have this sub-block valid and dirty, right? Now your coherence is at a finer granularity, and you might have the same block, but different parts of the block in different caches dirty at the same time. Now, if you had kept track of coherence at the block granularity, you couldn't have that, right? You could have only one of the blocks in one of the caches, valid and dirty.
So I guess my question is, does sector caches make any sense with when you have multiple caches? Because you really can't keep track of the coherence for each one of these.
I see. Well, for the smaller granularities. Well, you could, right? Why not?
Isn't that a lot of overhead?
It is overhead, yeah. It's certainly, now you need to compare the valid and dirty bits. But you could. It may not be that bad. It's more overhead because you need to keep the state, basically. This is essentially your state, right?
So then you have one cache line with multiple states.
Exactly, yes. Exactly, which is what this is, which is what a sectored cache is, really. One cache line with a single tag, so you reduce the tag overhead, but multiple different states per sub-block. Right. So you could think of extending. So this is actually really the coherence state, right? Think of it that way. But then you could decouple them. Your coherence state actually can be for the entire cache block rather than sub-blocks. So going back, so if you could actually get benefit, certainly, if you modify the coherence protocol. But if you don't modify the coherence protocol, you keep it at the sub-block level, you keep it at the block level, there are still benefits to sector caches, right? For example, one of the benefits that we've discussed for sector caches is when you're streaming and when you're writing data, right? In that case, you basically Or actually, one of the benefits is bandwidth savings, right? That's independent of the coherence. Let me pick up that example because that'll lead nicely to the lecture. You don't need to bring in the entire block, right? If you're going to touch only one sub-block in your entire block, you bring in that sub-block. And if you're not going to touch anything else, that's it. So this benefit, so you don't, basically you save bandwidth. This benefit is independent of the coherence, right? So sectored cache makes sense for that benefit. Does that answer your question?
Yeah.
OK, good. So these are independent benefits. But you can get better benefit if you actually do the coherence at a finer granularity, too.
So
Yes?
for this sector cache, when I do eviction, so it's just going to change one subblock or the entire line?
So again, that depends on your policy, right? If you want to evict the entire block, you could do that, right? Or if you want to evict a subblock, oh, OK. I guess what you're asking is when you evict a block in the cache, what happens?
Yeah.
Right. Well, that's if you do eviction, the eviction happens at the block granularity, right? You cannot evict individual subblocks, right? Because you have only a single tag, remember? If you had multiple tags, well, now you have finer granularity blocks, right? So eviction always happens at the block granularity. Well, one other benefit that we've discussed, again, in sector caches is when you're doing streaming writes. I'll go back to that. When you're writing a cache block, you don't need to allocate it, right, if you have a sectored cache. You basically write this first block, and you don't need to bring it from memory at all, because you just write, let's say, 8 bytes. And assuming you're writing all of those 8 bytes, well, at the same time, or maybe 4 bytes, you just make that valid and dirty, and you're done. Again, that's bandwidth savings. That's independent of coherence also. If you're just streaming writes, then basically you validate the first one, validate the second one, validate the next one, and validate the next one, and you have your cache block already written without going to memory at all. Whereas if you didn't have a sectored cache, you need to bring the entire block first, because you're not writing at a block granularity. Normally, instructions don't write at 64-byte granularity. Right? Okay. Any other questions?
So what is the difference between term line and way? Are they essentially the same?
The term line and what?
Way.
Way. So those are totally different, right? The question is, what's the difference between the term line and way? Line is the same thing as a block. Basically, cache line and cache block, those are different terminologies that have been used historically. But a way is really the granularity of associativity, right? Basically, if you have a two-way direct map cache, you have a one-way cache.
Yeah.
A cache block. A memory block, a cache block in memory can be mapped to only one location in the cache. Whereas if you have multiple ways, the same block can be mapped to multiple possible locations, as many as the number of ways you have in your cache.
It's like, I don't know, they use that saying like in 213 classes.
Way and line?
Yeah.
They shouldn't. No. Maybe you're confused. If they do that, there's a major bug. Yeah, so it's really, when we draw a cache, it's you have the tag store and the data store. And basically, the way is how many blocks can be present in the same index, right? You index into the cache with part of your address, right? This is the address. And this address can be present in, let's say, 2 ways, 2 different places. This is a 2-way associative cache. If this is 4, basically if you have 4 tags, 4 potential tag locations, this is 4-way cache, right? And your data store should be able to hold 4 ways also, right, in that case. So that's your way. This is a 4-way associative cache. Whereas a block is, this is a block, for example. Well, this is a tag, but this is a block. So in a way, you can host 4 different blocks in this case. Or in a way, you can host 4 different lines. Line and block are interchangeable. OK. I guess people can still see what I'm writing. Is this blurry on the screen?
It's a little blurry up there.
It's blurry over there when you look at your screen?
On here, it's not so bad. It looks blurrier
Oh.
in person.
OK, that's interesting. OK. OK, what else? Yes?
Are there any more sophisticated page replacement policies that's hardware-based?
That is what based?
Hardware-based.
Hardware-based. Are there more sophisticated page replacement policies that are hardware-based? That's a good question. I'm sorry?
Other than clock?
Other than clock. Well, clock is not necessarily hardware-based either, but, but actually clock was developed for software-based, right? Page replacement policy. It's a simple way of approximating LRU. Right? You guys are aware of the clock policy, right? OK. Basically, you have a bunch of pages in memory. And when you want to bring in a new page, which page do you evict? Ideally, you would like to evict the page that is going to be referenced furthest into the future. That's the optimal policy, Beldy's optimal policy. You've read that paper, right? Beldy's paper. But that's very hard to figure out, that optimal policy. Actually, it's impossible to figure out without knowing the future. So people have developed LRU as an approximation to that, right? Least recently referenced because of the referencing behavior that they've observed in some programs. But you know that that's not the perfect replacement policy either. So clock is a way of referencing, approximating even LRU. Basically, once in a while, you set a reference bit for each block. For each page, you keep a reference bit. And once in a while, you set that bit. That's called the access bit. And when the operating system needs to replace a page, it goes and tries to find a page that has the reference bit that is not set. Right? Well, you set the reference bit when you actually access the page, basically. And I guess you're right in the sense that it's better to do with this with hardware support because you don't want to trap to the operating system every time you access a page. So hardware support enables that. This is where virtual memory is nice, right? Hardware support, hardware accelerated virtual memory is nice because in the TLB, basically, you have a bit that says, I've accessed this page. Right? Without that hardware support, you somehow need to trap to the operating system, and that operating system needs to set that bit in the page table. And once in a while, those bits are cleared periodically, such that the stale referenced pages are not seen as referenced by the system. So are there other more sophisticated policies? You could certainly think about extending this, right? You don't need to have a single reference bit, but you can have a reference interval, if you will. And I think people have investigated that. I don't have the reference off the top of my head. But you could get closer to LRU, if you will. You could say this page was referenced in the most recent interval. This page was referenced in the next most recent interval. This page was referenced in the next most recent interval. So if you had 2 bits instead of 1 bit for reference or access, you could potentially do better. How much gain you will have, that will depend on the effectiveness of LRU on programs. Right?
What about non-LRU based?
So you could do random replacement. People have looked at that too. And in fact, if you looked at the lectures, random replacement actually performs as good as LRU on average across a large set of programs because of the thrashing behavior. Right? LRU is a terrible replacement policy if you're thrashing. Even if you have a cyclic reference pattern, right? You get 0% hit rate in your cache or in your memory. So you could certainly do random replacement.
Well, in
And-
caches, you have a lot of intelligent replacement policies.
Mhm.
Like reference interval prediction.
Yeah.
Like that. So do you have any equivalents in DRAM as well?
That's right, yes. Actually, people have looked at this a lot, at the systems community. We didn't discuss that because this goes a little bit into the systems. Although we're more than happy to discuss it right now, I think. Basically, there are similar replacement policies that have been developed for page replacement as well. One of them is ARC, and I think I'll give you a reference to that one. Basically, first of all of the replacement policies that are developed for caches can be applied to virtual memory also. Because virtual memory, if you think of it, well, DRAM, if you think of it as a cache, right? It's used as a cache for pages. in a demand page system. So you could apply all of those policies. And you can apply even more sophisticated policies for DRAM as well, because the page replacement is really done in software. Right. And some of the policies, I'll give you a reference. Let me try to find out. Let's do this. I guess I'll do this. This paper should have some references. Did I assign this paper as a required reading? OK, good. Have you read it yet? OK. And if you have ideas, you can certainly talk with Vivek. And now I know why I didn't want to open it this way. Right. OK. Let's do it this way. If I search for arc here, oh, that's not nice. There you go. A number of page replacement policies have been proposed to improve virtual memory performance. So I would encourage you to look at some of those. So yeah, clock with adaptive replacement, for example. This was published in FAST, File and Storage Technologies conference in 2004. And I don't remember what the idea was over there, but it's similar to the adaptive replacement policies that have been developed in caches. Except it's more, you can be more sophisticated at that level because you're doing it in software. At the hardware cache level, you need to be really simple, right? You cannot propose policies that take into account a lot of information and that require a lot of logic to implement. So this is one of the papers, but this is not the one I would start with. 18, 20, 30, 32. Let's see. Yeah, another one here. An efficient low inter-reference recency set replacement policy to improve buffer cache performance. Sigmetrics 2002. 20, 30, 32. No, not that one. Yeah, this one. ARC, a self-tuning low overhead replacement cache. So I would recommend that one if you're interested in that. Okay. So well, it's really for page replacement. But again, DRAM is a cache for pages. That's why it's called this, right? They basically have two different regions for memory, and they try to, as far as I remember, they try to keep highly referenced pages in one region and not so referenced pages in the other region, such that they can detect pages that are not referenced a lot in that region early. And if pages are referenced a lot, they move to this region. It's like garbage collection, if you know how garbage collectors work. It's at least generational garbage collectors work. You have some part of the memory that is used for nursery, if you will. And if an object dies in that nursery, you can just collect it and you just make that space available. If an object doesn't die for a given amount of time, and what does it mean for an object to die? Basically, there are no references pointing to that object. What people have found out is if an object dies, it dies really quickly. Basically, references for that object are, the object is deallocated really quickly by the program. So to take advantage of that, people have developed these generational collectors where they reserve a part of the memory space. Initially, the object is allocated from what's called the nursery, a part of the memory space dedicated for young objects. And during the lifetime of the object in nursery, and this nursery collection is common. When the nursery gets full or close to full, you trigger a garbage collection. And the idea is to find objects in the nursery that are dead. If an object is dead, you basically reclaim it quickly. If an object is not dead, you move it to an older generation. Now, the collection from the older generation happens much less frequently. Because what people have found out is that if an object dies, it's very likely that it dies very early. So you can keep this other part of the memory big and collect it less frequently and hope that many of the objects over there are not dead. Right? So you could do something very similar to cache replacement or page replacement. And that's the idea in this paper is very similar to that generational garbage collection idea.
Then should your map
Parallelism in what sense?
in DRAM, right? So you would interleave.
Oh, I see. So that's a good question. Basically, you're thinking of, so the question is, should your mapping to DRAM be based on parallelism or frequency of use?
Which is why you were talking about duality.
Yes, I was talking about frequency of use here. So that's I think you could also try to enforce that. That adds a little bit more constraint, right? In the sense that basically, I think what you're thinking of is where does a page map in the DRAM topology itself, right? You could add that to this replacement policy. This is solving an orthogonal problem. Which page?
You said you put it together in the contiguous region and then evict from there, the frequency used.
So I didn't mean not necessarily a contiguous region. So let me try to do this. Maybe logically contiguous, but physically not contiguous. Right. So you could, for example, oh, yeah, that's a good idea. Thank you. So think about this as your entire memory. And let's say you say this is your nursery, if you will, to detect objects that are not frequently used. This could be a logical view, if you will. Physical view might be part of what might happen is like parts of your memory can map to different banks, right? Let's say you have 4 banks. You can have this mapping. And also in the nursery as well, right? Does that make sense? So you could try to maximize parallelism with your allocation also. But I don't know any policies that have actually done that. I don't know if this makes sense. This is basically trying to show that the idea that I've described it at a different level than what you're thinking of. It's really your logical memory is partitioned between a nursery and an older generation. And those could be mapped in different ways, potentially, to the topology of the DRAM. And you can consider that in the allocation also. I guess page mapping policy is to maximize memory level parallelism. I'm not sure if I remember any such policies. Do you know any?
I thought that's what they all do.
Well, usually a page replacement today is not aware of the topology of DRAM. Now, we propose some of the mechanisms that you're going to read that tries to partition channels, for example, across different applications, such that applications that go badly with each other don't interfere with each other. But today, in today's systems, when you do a page replacement, it's really which page you're allocating is not really aware of which DRAM bank that page resides in. So that information is not taken into account in today's systems. In NUMA systems, there is some. Like if you have a non-uniform memory access, the NUMA-aware operating systems take into account whether the memory is coming from a local DRAM versus a remote DRAM, because that has a huge difference. But within a single node, as far as I know, there are no operating systems that are aware of the topology of DRAM. And this could be a good, interesting research topic, actually. Figure out how much this matters, and can you develop a better policy? I'll point you to a couple of papers that have looked at parts of it. Let me actually do that now. Actually, I will recommend some of these papers later on too, but let's see. I guess it's going to be easier. Oh, I guess I cannot search. Yeah. So this one, in this one, the idea is to partition the memory channels across different applications. And we'll have a lecture related to this if you haven't already watched it. This is in Micro 2011. Basically, instead of allocating channels to different applications, pages, in an application agnostic manner, try to figure out which applications interfere with each other badly, and you know which applications actually interfere with each other badly. If you have a memory scheduler that's doing row hit first scheduling, an application that has a lot of row hits degrades the performance of another application that doesn't have a lot of row hits, right? A streaming application versus a random access application. If you put them together, one of them slows down significantly, right? So if you separated them to different channels, now both applications have good performance. And that's what this paper tries to do. Based on the application characteristics and how they interfere with each other, separate them to different channels. If an application is memory intensive versus another application is not memory intensive, allocating pages for both applications from the same channel degrades the performance of the memory non-intensive application. Because memory non-intensive applications requests get stuck behind the memory intensive applications requests. So whereas if you separate them to different channels, now the memory non-intensive application can make progress fast. And that's another rule in this paper. These are two heuristics that are used to change the page replacement policy and page allocation policy to partition pages across different channels and partition applications across different channels. Now this does it at an application level, and it's not a hard partition because if an application needs more memory than a channel, you don't want to limit it to that channel. Otherwise, you'll start getting page faults, right? That's not a good idea because the trade-off should not be interference versus page faults because page faults have huge latency. So it's really a heuristic, a preferred channel. Each application is assigned a preferred channel. Yes? Yeah.
So this paper try to mitigate interference with your channel partitioning. So is it possible that we partition the application in the granularity of bank?
That's right, yes. Yeah. And there's another paper that I'll recommend related to that. You can certainly partition in the granularity of a bank, but it gets a little bit more complicated, and the benefits may not be as high. So that was the other paper that I was going to give you.
Because for a single channel, two applications may not necessarily interfere with each other, but for a single bank, if there are two applications.
That's right, yes. That's right, exactly. That's a good observation, basically. If you have single channel, this doesn't work, right? And maybe you want to, because if you have a single channel, you cannot partition at the granularity of channels, obviously. And even if you have multiple channels, you may want to separate the applications in the banks such that they don't get bank conflicts, right? And this paper proposed a mechanism to do that. It's balancing DRAM locality and parallelism in shared memory CMP systems, HPCA 2012. Actually, it'd be good to put some of these papers, perhaps, after a discussion. Maybe I'll open it up. So what this paper does, actually, is interesting. It does what you are saying, but it statically partitions banks across different applications. So it's not dynamic partitioning. So it's a little bit, it doesn't go the full way, if you will. Maybe you can do better with dynamic partitioning of channels. So one problem with this approach in general, partitioning channels, is if you made the wrong choice, like if you partitioned your channels, it's harder to recover. The cost is higher, right? Because you need to move the page from one channel to another channel, or one bank to another bank. And that's costly in today's systems, right? Because it's an entire page, 4 kilobyte page. And that movement takes time.
And for a detailed question, so it's that kind of migration from one bank to another bank. So it's like the latency of one read plus one write.
That's right, exactly. And you do it for 4 kilobytes.
4 kilobyte, but that 4 kilobyte may be in the same row.
That's right, basically. But it could still take a long time, right?
Yeah.
Yeah, 4 kilobyte divided by, basically, let's say you do an 8-byte burst. It's still a lot of accesses, right?
Could we do that, like a copy of one row in one?
One shot?
Yeah, one shot.
Not across different banks. Although one of the papers that I will talk about in one of the lectures is RowClone. And the idea is copying an entire row to another row. The question is, how do you do that? Well, if the rows actually share bit lines, then you can do that, right? And actually, I was going to talk about that today, but that's okay. This discussion is good too.
That is because by the way, it's like sorry. So for different banks, when they connect with each other, it's like a 64 bytes.
That's right. Yes. Yeah. In DRAM, if within a bank, you have actually within a subarray. Remember, DRAM is divided into subarrays. Have you watched those lectures? Has everyone? Yes? Yes? It was this week, right? That we were. OK. You have to keep me on my toes also, because when you record these lectures and put them up, I don't exactly know when they were due. But basically, DRAM is divided into subarrays. And, well, actually, let me pull up what I was going to talk about briefly. Maybe what I'll do is this. I'll go into the backup slides here. Oh, maybe not. Huh. OK, let's do this one, I guess. Yeah, right. If you look at a DRAM bank, it's divided into these subarrays, right? And these subarrays, within a subarray, you have these bit lines that are local bit lines. And basically, you transfer, and there are lots of those bit lines. Actually, maybe I'll. These are not organized that well, huh? At least it's indexed in a way that, yeah, this may be better. Yeah. Within a subarray, you have these global bit lines. So if the two rows, 2 pages are in the same subarray, you can copy them through the row buffer, right? Whereas across these subarrays, you actually have fewer bit lines. This picture is actually incorrect. You don't have all of these global bit lines coming into the global row buffer. You have actually a smaller number of bit lines. So when you want to copy from one subarray to another subarray, it's done at a much smaller granularity, because we have much fewer bit lines. Does that make sense?
Yeah, and this is within one bank.
Within one bank, yeah.
Different bank, it's also the same thing.
Exactly, it's the same thing. Basically, you have this global circuitry that is much thinner, much narrower than your local bit lines within a subarray. So it takes a long time.
Is it the size of a supercell?
Say it again?
Is it the size of a supercell you copy from one bank to the other?
What is a supercell?
It's also a notation to think about this. Like, I don't know, they partition the bank into like supercells. One supercell contains like when they copy data from memory to cache. Each time it's a supercell. It's a supercell size.
You mean a block, or?
It's like 64 bytes.
Yeah, that's a block. That's a cache block. I don't know what a supercell is.
I don't know.
Yeah.
So, yeah, they use that term. So.
Who is they?
213.
Okay.
That class. So.
OK, that's interesting. Yeah, I'm not familiar with that terminology. But yeah, it's a block, right? It's a cache block then. Well, it depends. It's not necessarily. No, it's not actually. It's much smaller than a cache block. So it could be 64 bits, for example, here. 8 bytes, right? Whereas this local row buffer, it could be 1,000 bytes, right? Oh, 1,000 bits, sorry. Yeah, instead of 64 bits. Yeah. So usually a good number is local row buffer could be 1,000 bits. And global row buffer is actually 64 bits. Yeah. This picture is misleading in that sense. OK. So what was the question? How did we get into this?
So migration between different banks is very expensive.
That's right, exactly. Migration between different banks is therefore very expensive. And I was going to show you something related to that, but I cannot find it here. Yeah, migration between the same bank, let me actually show that, is really cheap, right? What you can do is, basically, this is your DRAM operation, right? You activate a row. To read 1 byte over there, you need to activate the entire row. And what happens is you transfer the entire row into the row buffer once you do an activate. And then you do a read operation, right? And the memory controller sends a read command. With RowClone, one of the papers that actually I may have described in the lectures, RowClone takes advantage of this fact. Basically, you activate, if you want to copy one row to the other, you can activate the first row, which basically brings the data into the row buffer. And once that's done, you can activate the destination row. Right. Now, the data that's lashed into the row buffer starts driving the cells in the destination row once you do that. Does that make sense? Because you've activated the row, and there's a stronger charge flowing from the row buffer into the activated row. So the cells capture the data that's in the row buffer.
So it's kind of eliminated the pre-charge step between these two.
Exactly, yes. If you had the pre-charge step, then you cannot do this, right? And once you activate that, basically, the entire row is copied from here to here. That's the idea of RowClone. So this makes the copy very cheap. You can copy one row to another row if they're in the same subarray. This is the local row buffer in the subarray. Very fast. This actually, we should make this paper available too. This is going to be published at Micro in 2013. Vivek Seshadri is my student who developed the idea. Basically, this, I guess I'll give you some more concrete numbers if I had it, but I don't have it here. Yeah, basically the latency of a row buffer, row copy goes from 1046 nanoseconds to about 90 nanoseconds. If the source row and the destination row are in the same subarray. If they're in different banks, then latency savings is not that much. Right? You could still do the copy in DRAM, right, if you have memory controller orchestrating that copy. Here, you do copy purely in the subarray. The memory controller says, subarray, copy this row to the destination row for me. And the memory controller has two commands, activate and activate. And that's done. Today, you cannot do it in today's DRAM because you cannot issue two consecutive activates to today's DRAM chips. So you'll need some modification to today's DRAM chips. The reason you cannot issue two consecutive activates is the DRAM doesn't know, at least it's not specified, what will happen to the first activated row. Because you activate one row, row buffer has its contents. And if you activate the next row, actually, I think the behavior is unspecified today. Because what will happen to the firstly activated row in that bank, right? Well, the proposal with RowClone is that the second activate serves as an implicit deactivate for the first row. Basically, that gets deactivated, and the second row gets activated. As a result, you get this copy effect. So it's relatively low cost. Actually, we should make this paper available, perhaps, right? If you, did I assign this? I don't think I assigned this. But I've described it in the lectures. Maybe you haven't gotten to that yet in the DRAM lectures. OK, we will give you a copy. Brian, could you remind me? Let's see. Actually, I'll give you this paper. Not this guy. Yeah, there you go. It's going to be something like this. But I've given you the basic idea, basically. And if you look at the latencies and energies, this is what you get, basically. In the baseline, for a 4 kilobyte copy, it takes 1046 nanoseconds. If the Vivek called this a fast parallel mode. Basically, if the source and destination rows are in the same subarray, you get 90 nanoseconds for the copy. And this is the energy. This is microjoules, 3.6 microjoules for the entire 4 kilobyte copy in the baseline. So in the baseline, what would happen? In the baseline, if you need to do this kind of copy, basically you need to read the source row byte by byte and save it to the memory controller, and then pre-charge the array, and then byte by byte write to the destination row, right? That's what you need to do in the baseline. Instead of doing that, byte by byte read of 4 kilobyte page, and then byte by byte write of a destination 4 kilobyte page, you do this in one shot by taking advantage of this internal parallelism within the DRAM subarray. Okay. But if you look at this, if the source and destination rows are in different subarrays in the same bank, this is your latency, 1050 nanoseconds. It's very similar to the baseline. It's a little bit higher because of there's additional overhead. So if doing bulk copy across different subarrays within the same bank takes longer.
But it seems that for different bandwidth is smaller.
That's right. Because why? Because if you're in the same bank, you're sharing the global bit lines, right? You cannot read and write at the same time.
Yes.
Whereas if you're in different banks, you have two different global bit lines. You can read from one bank and write to the other bank concurrently. Does that make sense?
Oh, so it's like a pipeline?
Exactly. It's pipelined. And you can do reads and writes in parallel. Whereas if you're in the same bank but two different subarrays, you have to read first and then write afterwards. You cannot pipeline them. Okay? Now, if you're in different chips, now it becomes worse, right? If you're in one channel, in one DIMM, and another channel, in another DIMM, well, you can still pipeline it, but you have to go through the interconnect and copy the entire page. So your penalties will be similar, same as the baseline, basically, because there's no support in DRAM. If you're in different chips, certainly you cannot support the DRAM chip, right? So we came here because of the page migration policies, right? So it's good to discuss this. But going forward, I think looking into support for page migration is very interesting in DRAM, because you may want to move data for different reasons. And how to do that more efficiently in systems is important. So this one provides support for page migration or page copying within a DRAM chip. How to do that more efficiently across DRAM chips at the system level is another interesting topic, I think. And this one works, obviously, if the source and destination pages are allocated in the same subarray. If they're not, if the operating system is not aware of this, maybe you don't get much benefit from this, right? So going forward, looking into mechanisms that can allocate, that are aware of the DRAM structure itself in page allocation is interesting. This is something you mentioned earlier. I'd be interested in thinking, like brainstorming more about that. I think there are potential possibilities over there. OK, let me get back to one more thing. I had some other paper in mind as well that I'll recommend. So this was the other one. And we'll put the RowClone paper as well. I don't know what the sense thresh EPS means, but OK. There's another page level or channel level allocation mechanism that we have looked at. Which is this one, application to core mapping policies, again, to reduce memory system interference in multi-core systems. The idea over here is how do you actually place the applications on a grid-based multi-core system to minimize memory interference? And what is a grid-based multi-core system? It looks like this, right? Basically, you may have 64 cores and 4 memory controllers. And it could be like a two-dimensional mesh like this. And you may have 64 different applications, for example. And the question is, how do you map them to these different cores to minimize the interference that happens in the memory system? And here, the assumption is that we partition maybe not hard partition, but soft partition, have preferred channels. For those applications that are mapped here, they go to this channel, this memory controller. Those applications that are mapped here in this quadrant go to this memory channel. Now, you could have a random mapping like this. I believe this is random. That may not be a good idea because applications that heavily contend with each other may be mapped similarly. Or you could have something like this. Actually, the first one is random mapping. What is C? Imbalanced mapping. You could get unlucky, right, if you do random. You could have all memory-intensive applications mapped to the same channel. Then you don't have good utilization in other channels, right? You have a lot of interference here because the darkness indicates how heavy an application is in terms of accessing memory. And lighter applications are accessing memory less. So if you map all of the dark applications here, then you have a lot of contention in this channel, right? And if your page allocation policy is not aware of application characteristics, and your mapping policy is not aware of where an application is mapped, and it's not aware of application characteristics or the topology, then you can get into a situation like this, right? So this is more showing the balanced mapping. So balanced mapping tries to balance load balance across memory controllers. That may be better than this one, certainly, but it may not be the best. Why? Because it may also make sense to actually have some of these applications that are latency sensitive or that do not interfere with others that much, but still need some memory bandwidth mapped to their own quadrant such that they can keep their cores busy, right? And balance the mapping across the other quadrants. So that's kind of the idea in this paper. This is for a particular system, of course, in this picture. But you can generalize the idea. So in this case, of course, you still need page allocation policies. For the applications that are mapped here, you allocate from here. But what if those applications actually exceed the memory present in this channel? What do? Right? Then you need to spill somehow. You need to allocate the pages of that application from some other channel. So after some point, your mapping may not be good because you may have pages that are located in all the channels, right? Then the question is, how do you actually fix that problem? It's difficult to fix. It's not easy because now you have pages allocated across all the channels, but you're also trying to map an application's pages to the same channel, right? You'll need to gather the pages to the same channel, perhaps, right? So there's no solution in the paper to that, but that's in general the difficulty with page mapping or page allocation mechanisms. If you want to use that to reduce interference, for example, or maximize performance in some way, if you made the wrong decision, or if later dynamic conditions led to spreading of the pages, how do you actually go back to a partitioned, go back to a better scheme? The cost is high to move the pages around.
So where would the benefit lie using the software to do all of this or the hardware?
Using the software to do what?
The mapping and eviction.
For pages? Well, I think software in general has higher overheads, right? If you don't have any hardware support, for example, it's a lot of overhead to figure out characteristics of a page. How many times it's accessed. Even how many times it's accessed is hard, right? Because if you don't have any software, any hardware support, you don't even have that access bit with every access. So that's the general. I would say software has a lot of overhead in identifying dynamic usage of the pages, and also a lot of overhead in moving the pages because you need to go through the operating system code. Whereas if you do it in hardware, you can adapt to dynamic changes much frequently.
But you could argue that the software might have better visibility.
Exactly. Yes. That's another fundamental distinction between hardware and software. Software can have a lot better visibility. It can collect much longer-term information and keep it in the page tables, for example. You're absolutely right. So it's not clear what the best policy is. I don't think it's purely hardware. I don't think it's purely software. It's, again, it needs to be hardware-software cooperative.
hardware to determine the state of our memory and expose that information to the OS.
That's right.
So that we can
Exactly, yeah. If the hardware collects information, for example, at the finer grain time intervals, and expose that once in a while to the OS, or the OS can query it, or maybe the application can query it, you can do much better page allocation at the software level, perhaps.
But right now there is no such kind of hardware we can use. We need to add.
There's no such hardware you can use right now, you're saying. Yeah, as far as I know, there's no real system today that collects information per page level and exposes that to the software.
And it's also not so expensive to collect it in the granularity of page.
In the hardware?
In the DRAM system, use hardware.
Well, it depends on what you're trying to collect, I think.
Yeah.
If you want to collect information about all pages, then it's a lot of hardware overhead, right? But if you want to collect information about hot pages, maybe it's not that much hardware overhead, if you can do that somehow. Yeah. These are actually very interesting topics. I can recommend you some more papers. Actually, let me do that while we're at it. And Brian can add these to the web page, because there seems to be a lot of interest in this. And I think there are a lot of possibilities here. Let's do this. I guess what happens if you do this micro pages? There you go. This is something else I would recommend. It's called micro pages, increasing DRAM efficiency with locality-aware data placement. Let me see if they have a single figure with a basic idea. You might. Well, maybe not. OK, I don't see it. But the basic idea here is, let me try to draw that figure dynamically. Oh, I guess you won't be able to see it. Can you see it now? Can you see something now? OK, something. Let's see what happens when I draw something else. OK, so if you think of a bank, OK, that's not too bad, right?
Must be like rotated.
Why is it rotated? Let's see. OK, I'm going. OK, that's better. OK, so if you think of a bank, today what happens is you buffer a page in the row buffer, right? And you exploit locality in that page. But if there are two hot pages, you need to buffer one page, exploit locality, and then buffer another page, right? And if these hot pages are utilized in an interleaved manner, you access page A and page B. So if your accesses are A, B, A, B, A, B, A, B, dot, 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 and if the interval is relatively far away from each other, memory scheduler cannot exploit locality. And you basically get activate, precharge, activate, precharge, activate, precharge on A and B, right? If the accesses are separated farther apart in time. If the accesses are close by in time, the memory controller can look at its queue. Basically, what it can shape this access stream such that it's A first, and then B, 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 B next, right? By doing row hit first scheduling. But if these accesses are far apart in time, what might happen is you access A, a little bit later, you access B, so the memory controller needs to precharge and then activate B. So the idea with micropages is what might happen is actually something like this. A might have a hot portion here, and B might have a hot portion here. The idea of micropages is combine them together, right? Basically, put the hot portions of pages together, like this A hot and then B hot, right? So that when you open that page, both of them, oh, yeah, thanks. Both of them will be in the row buffer, and you can keep hitting in the row buffer. That's the basic idea. And you can keep extending this idea, right? So you can have multiple subpages within a row buffer. Then the question is, how do you do that? Well, you will need to collect information at the subpage level at the memory controller, right? Because you don't want to do this in software because there's a lot of overhead. Whenever you need to access a page, you need to increment a counter, right? Figure out which ones are hot. But you will need to do that in hardware. And the paper doesn't discuss this issue, but this is something interesting to think about for you. I guess food for thought. How do you keep that information? I like the idea because it's cute, right? It's nice. It makes sense. It's like an intuitive idea. But then how do you implement it with hardware support? That may get a little bit tough. Although there are other papers one more that I would recommend, that try to determine what's a frequently used page. And it's actually from the same group, Rajiv's group. Or maybe that's what I'll do. No, Chrome doesn't like me. I guess let's do this. This is easier. It's good to have a single repository. Yeah. So this paper proposed a data structure. No, I don't want that one. That identifies frequently used pages in DRAM. Filter-based. It's basically a filter. Yeah. I guess it's kind of the idea, or at least the approach. Yeah. Basically, when you're bringing a page, you figure out hot pages and place them in this DRAM cache. And you keep others in main memory. Then the question is, how do you actually design this filter? Right? It could be a sampling-based filter, for example. Once in a while, you flip a coin and decide to keep track of that page in this filter. Because if you keep track of every single page you access, then this filter will become huge, right? Because you like to figure out which ones are hot. What you can do is you sample. Once in a while, whenever you access a page, you keep track of the information. And the hope is that if there are actually hot pages, those will be captured in the filter, and you'll be keeping track of those hot pages, right? And their access counts. And the paper discusses some of the design issues related to that. So there could be ways of building this hardware. I don't know how we got into this, but I think somebody asked what could be the overhead, right? But this is another paper I would recommend. It doesn't talk about page allocation at all, but some of the hardware that's discussed here can be used for keeping track of information at the page level at the memory controller. So this is another general technique, like sampling, right? If you're trying to figure out what's hot data, you don't need to keep track of every single page or data element you access. You can do sampling. Meaning you don't, basically only once in a while decide to, I'd like to keep, let's say you have accesses to, okay, pages A, B, A, B, A, lots of A's, right? Let's say you say, I'm going to keep track of every fifth page. Well, this is that I access, right? And ignore all the intermediate accesses. Well, if you have hot pages, you will actually keep track of the hot pages this way, right? Because by definition, a hot page is accessed more often than others. And if you're keeping track of every fifth page, you're going to capture the accesses for that page. Right? So sampling is a nice way of building simple approaches that can filter out non-hot pages. Right? And reduce your hardware cost also. OK. I guess you've seen sampling with the memory level parallelism over cache replacement. Right? We've discussed another use for sampling. Basically, instead of keeping track of every single set in a cache, you sample the sets. Then the key question is, how do you determine which sets to sample? Right?
So what's the difference between that mechanism and set dueling?
OK, so that's a good question. So set sampling came earlier. This was the memory level parallelism over a cache replacement paper that we did with Moynihan and Qureshi. Set dueling, so one of the disadvantages of set sampling is what it does is for a given number of sets, you implement multiple policies, and you try to figure out which one does better. Right? Which means that for a given number of sets, you need to implement both policies at the same time. Set dueling, which I don't like as much, not because I didn't participate in the development of, but because I think the characteristics is not as nice, but it does have an implementation advantage. OK, I guess pictorially it's nicer. In architecture, it's usually better to use pictures than words, I guess. I guess it was Confucius who said a picture is better than 1,000 words, right? Maybe 1,000,000 words. But when I think of set sampling, I think of this. Basically, you have a bunch of sets, all sets in your cache. You pick a bunch. Let's say you pick these sets, right? And now you need to implement two policies. Let's say you're trying to figure out which one does better, MLP aware or LRU, right? Now, all of these sets need to implement those two policies. Whereas set dueling, you pick different sets. It's like a duel. This implements MLP aware, and this implements LRU. Now, the nice thing is here, the implementation cost is better because you don't have two auxiliary tag directories for either of these. You have only one. MLP aware here, LRU here. The downside, I think, these are apples and oranges, right? You're really comparing. Here you're comparing apples to apples because it's the same set that you're running two policies on and comparing the results. So hopefully you have better confidence as to which one is doing better. Whereas here, you're comparing set apple to set orange, and you're trying to compare two different policies, which may not really give you good results. I guess here you're relying on the uniformity of behavior of different policies across these different sets.
You have more than one set?
Yes, you have more than one set. So in either case, the number of sets should be large, should be reasonably large. And you have some of that analysis.
Might not be there because you have more than.
That's right, yes. And as you add more sets, you add the entire cache, right? And both of them rely on, both set sampling and set dueling rely on the representativeness of the set. So if the sets have uniform behavior and they represent what's going on in the entire cache, that's great. That's true for both. But here you have an additional reliance on that. But yes, that's actually the argument, basically. You have uniformity in the behavior and you have enough sets, then this makes sense. Yes?
So on this topic, the graph on slide 40 that shows the instructions per cycle for the two policies, the MLP aware and the LRU, as well as the hybrid.
That's right.
So the hybrid turns out to be performing better than, like significantly better in some cases than either one of
That's
the
right.
original ones. So what is that due to?
Which slide is that? Let me open this up.
40?
Number 40. So we'll go to course. Oh. OK. Modules. Which module?
3.4.
3.4. This one, right? I'll open PPT, I guess. Number 40. Okay. Oh. Came up.
You go with the question.
Oh, okay. So the question is,
That looks different.
this looks different?
Not the same thing.
Same slide 40?
This doesn't plot the. Yeah, like we had it there.
I had it there?
This.
Which one?
Are they numbered differently? The one that has a third line, it has 3 lines.
Oh, yeah, this is it, I think. Oh, wait. This does look different. Look at that. How did that happen? I thought.
Is there an animation?
Is there an? Oh, yeah, there's an animation. You're right. Okay, yeah. Okay. Wow, we're not going crazy here. Not yet, at least. Although with PowerPoint, you never know whether you're going crazy or PowerPoint is crazy. Okay. Yeah. So you're saying basically the question is, this is slide 4. Well, people are seeing the slide. At this point, the linear policy is better, which is MLP aware policy. And after some point, LRU becomes better. And your question is why?
No. So and then the third one,
Yeah, this is the hybrid.
the hybrid, like let's say 150
Uh-huh.
instructions, it's better than either one.
Oh, I see. It's better than either one. That's a good question. Why could that be? I'll have to think of that. Well, even here, right?
Yeah, I was thinking this implies that there's a phasing of this application that's
Yes.
smaller granularity.
Exactly. Yes.
If you zoom in, it should actually track one of them.
Exactly. Yes. So you're right. That's the reason. So this is the granularity at which we plot this is different from the granularity at which the hybrid policy adapts, which means that the hybrid policy can have better performance at any granularity. That's the main reason. There may be other reasons, but I cannot think of them right now.
It's explained in the paper.
Yes.
Same reason is explained in the paper.
Okay. Yeah. That's. Yeah.
Not yet.
Did we assign this paper as required reading?
Already reviewed.
Oh, okay. Already reviewed. So, by the way, if you're late in your paper reviews, that's okay. Please do the paper reviews. Actually, that's okay is too strong, perhaps, because you'll have a lot of backup paper reviews. So in that sense, it's not okay. But do the paper reviews. Doing the paper reviews is actually what we really care about in the end, because that's for your benefit. Obviously, we're not going to be able to ask you questions on all of the papers, but hopefully that's for your benefit going into the future. Yes. So that's a good hypothesis, and that's actually what's happening here. If you had actually had this at the granularity of adaptation, which is actually difficult to do, because the adaptation happens at a cycle-by-cycle granularity, right? You can flip between one policy and the other at a cycle-by-cycle granularity. Then you wouldn't see this anomaly, I think, unless there's some second-order effect that happens. But that's a good catch. That's exactly what's good to do when you read a paper. Look at a graph and say, wait a minute, is this actually what I should be expecting from this graph? And if the granularity of adaptation was exactly the same as what the granularity of plotting in this, you wouldn't have expected that. Okay. What else? I guess I'm not going to talk about what I intend to talk about, but this is also good because what I intend to talk about is more of a general thing that brings a lot of memory lectures together. Anything else? I was going through some. Yes?
Cache compression. So the compression ratio seems to be the bottom line metric of interest, but I was just interested about like an intermediate metric which would show what is the percentage of cache lines to which the compressor could apply, because for some it doesn't apply, right? Because we're considering only limited ways of compressing. So some cache content just cannot be compressed, it has to be left decompressed. So is there data on this? So how much opportunity is not being exploited because we're limited in the kinds of compression that we're allowing?
I see. So let me try to understand your question better. So you're saying the kinds of compression. When you say the kinds of compression, it's how many bytes of base and how many bytes of delta that we're considering in the compressor? Well, that's a good question. I see. How would you do that ideally? For example, we're not considering bases that are 8 bytes and deltas that are 1 bit or 2 bits or 3 bits. We're looking at a granularity that's coarser than that. That's it, right?
I was thinking, so let's say you fix the number of bases or something. Then then you just left some potential compression gains on the table, right? Just by doing this.
Just by fixing the number of bases, yes.
Number of bases, yeah. Which I think is the same thing that you were saying earlier.
That's right.
If you fix some parameter of your compressor, then there's some lines that you won't compress, even
That's
though
right.
you could have compressed them if you had a different compressor.
That's right, yes. So I think the ideal mechanism was not investigated, at least for the base delta immediate compression. You're thinking of base delta immediate compression, right? Yeah, I don't think, actually that's a good question for Gennady probably, who did that work. I don't think he investigated granularities that are smaller than a byte, for example, for deltas. But it's certainly that you can compress at a smaller granularity. Your deltas could be 4 bits, right? There's no reason for that. I don't think he investigated that. So I don't think that value is there in that paper. But other compression algorithms, so ideally you would like to look at the entropy, right, in the entire cache. But that's also difficult to do. So I don't know the answer to your question. There are some sensitivity studies. At least let's. Yeah, comparison to the optimal compression ratio. Yes, that's a good question. Yeah, I don't think there is that comparison. There's a comparison with multiple bases, as you've seen. There's comparison to other techniques, but not to the ideal compression ratio. Yeah, I don't think so. But I think you can, if you're interested in this, why don't you talk with Gennady? You have his contact information, right? It's in the paper. He's one of my PhD students. And he'd be more than willing to talk with you about this topic. It's his passion, so. maybe he'll come up with some ideas also, who knows? This is another very important topic actually going forward. Because memory is not going to get that cheap. It's going to become increasingly expensive. And we'd like to not waste any of it. So how do we take advantage of the limited memory we have in a more intelligent way? I think compression is a very interesting way to do that. Maybe you guys can think of other ways of doing it too. What else? We're almost out of time. I guess no questions online. You've been pasting the papers. Okay, shall we have a discussion Friday, or is this enough for the week? I guess I like asking this question all the time. What do you all think? What do you think of the lectures in general? Are they useful, understandable online? Yes? Yeah. Who wants to have a discussion on Friday? No one? Are the discussions useful too? Not so much? You'd prefer lectures during discussion?
Yeah, I think like you mentioned like almost every one of these discussion sessions that you kind of have like something planned and we never get to that. And I feel like that
Yeah.
might actually be more useful because I feel like a lot of what we do in recitation is just answering
Yeah.
people's questions.
Maybe we can do that on Friday.
Yeah, maybe we can do that Friday. Yeah, if you want to do that. Okay. Yeah, let's do that on Friday then. Well, the purpose of recitations are actually this, but I'm happy to do that on Friday also. Let's go through that, but it will be similar to what I've covered in lectures. Actually, going forward, I think we'll have some lectures that are in person as well as live. So hopefully that'll make some of the recitations even more appealing to you. But come up with some questions yourself too. Not to put you on the spot, but that'd be good too. So okay, I guess let's plan on having a recitation on Friday then, and I'll think about covering only what I intended to cover. And if you have questions, we can still try to do that, but we'll defer most of the questions to next Wednesday. Is that good? Okay, I guess I'll see you on Friday.